In this video, we're going to examine a 1D column, vertical flow, transitioning between two steady states. The difference is that the top boundary will now be a type 1 Dirichlet defined head boundary. As for the last video, we're going to look at the head distributions through time. We're also going to look at how the flux changes at the top and bottom boundaries through time. What happens if the top boundary condition is a type 1 constant head boundary? For this condition, the head has to transition from its high value at the top towards a zero gradient, and the gradient must again be decreasing continuously with depth. So we have a very high gradient at the surface, decreasing to the initial gradient at some depth. Again, beneath this depth, the column still hasn't felt the impacts of the change in the top boundary. Just as for the constant flux top boundary case, we have a change in gradient with depth. That means at any location, we have more flow coming into that location from above than we have leaving from below. That means, of course, that we're going to have an increase in storage at that depth, and therefore we would have an increase in pressure with time at that depth. The result is a rightward shift of the pressure or hydraulic head profiles, and that gets muted in time, moving towards the straight steady state distribution that we would see at the final condition. So that just leaves us to think about what the flux looks like as a function of time into and out of the column for this type 2 top boundary condition. It turns out that it looks quite different. The top boundary, now rather than having a step change, has a very high gradient when we first change the constant head boundary condition. We have a very large downward flux, and then that decreases with time as that gradient at the surface decreases to the final gradient. The bottom boundary has the same shape. There is a delay, and then it slowly comes up to the final gradient. But if you notice, that actually happens much faster in this case, because that early high gradient is driving much more water into the column than the type 2 boundary condition. Just as before, steady state is defined macroscopically as the time that the inflow and outflow are equal. It also represents the time that the inflow and outflow are the same at every point in the column, and that there is no longer any change in storage with time in the column from the flow equation. And that area between the curve, even though it has a different shape, it still represents the change in storage. And because we have the same initial and final conditions, it must be exactly the same amount of storage change.